under the title of Basic Incidence Theorems in Euclidean Geometry, I've talked about the TEZER theorem and presented for contrast its so-called incomplete form. I proved it as an application, I should say rather elegant application of theorem of Menelaus. And then we discussed what the adjective incomplete meant, how it could be alleviated, how you could make it into a complete theorem, and I gave you first indications of the fact that there are certain theorems in Euclidean geometry which simply just scream to make it clear that they are not at home in Euclidean geometry. They need a larger geometry. And that was our first indication of a larger geometry, which is lurking behind Euclidean geometry, the so-called projective geometry, okay, which was obtained by taking the Euclidean plane and adding to it a line consisting of ideal points, so-called points at infinity. Right, okay. Now, I would like to present yet another basic theorem of incidence. I will present it within the framework of Euclidean geometry, and it will, of course, of necessity, for the very same reasons, of necessity will be an incomplete result. I shall leave it entirely to you to imagine, to describe for yourself how to make it complete by obtaining special cases, by putting this point or that line to infinity, at infinity. So that's entirely left to the student. So I am presenting you the theorem of Pappus. Pappus, an ancient result, yet it has proven itself, it has turned out to be of central importance, so central as to be chosen in certain treatments of geometry as an axiom. It's absolutely basic, and it's closely related to the theorem of TEZER. We shall see that later. Theorem of Pappus. Theorem of Pappus. So let me Pappus is a Greek mathematician who lived sometime around 320th year of our time reckoning in Alexandria. Iskanderia, as we call it, Alexandria. Okay, Pappus. And the theorem he discovered is more or less this. Given, okay, so I take distinct lines. Let's say KK prime. And distinct points. Well, there will be 6 points. The first 3 will lie on the line K, and the latter 3 will lie on K prime. Okay, so given this configuration, F. Now I have to make a list: BC prime and B prime C. Okay, so this pair of lines, CA prime and C prime A, that pair of lines, And finally, as you may notice, I can go blindfold. I'm doing it in cyclic fashion, AB prime and A prime B. Intersect in X, let's say, Y, let's say Z, respectively. Then these points are collinear. I'm not quite sure if this is the best formulation, X, Y, Z, are collinear. I mean, thinking about it, I think I can give a better formulation, but never mind that. X, Y, Z are collinear. Okay, now once again, this is a result which you can make from which you can obtain special cases by pushing any of the points A, B, C, A prime, B prime, C prime into infinity, or taking any one of the lines, let's say K or K prime, and making them as the line at infinity. So there will be a huge, really inscrutable set of special cases. So, you know, that's the burden you have to carry if you insist on Euclidean geometry, if you insist on the geometry without a horizon. So there it is. Yet if you make this condition that these lines should intersect in X, Y, and Z, then these points are in fact collinear. Now let me do my best and give you a diagram. Let me see. Okay, there we are. Okay, so the two lines, K and K prime. There we are. So so K is something like this, perhaps. And I shall, of course, take 3 points on it. 3 distinct points. And another line, K prime. Okay. And, A prime, so that's K prime. Well, A prime, B prime, let's say, C prime. Okay? Right. And then we have made the condition that the line B prime C and BC prime should intersect in a point X, and CA prime, well, that's easy to learn by heart. C prime A should intersect in a point which we shall call Y, and finally A prime B and AB prime should intersect in a point which we shall designate Z. There we are. Okay, the point X, the point Y, and the point Z. Okay, so we would like to prove that X, Y, and Z lie on a line. Well, and I promised you that this shall be done as an application of the theorem of Menelaus. Well, of course, you all know that in order to employ the theorem of Menelaus, you must have a triangle, and the points you are dealing with should be lying on respective sides, so on and so forth. But there is no such triangle in this picture. Well, let me make that triangle. Let me start with that. So let us assume furthermore, I mean, that the line C, okay, C, right. Let's CB prime and BA prime intersect in a point which I would like to call V, for reasons to appear in a minute. Okay, so what is the triangle? Okay, and I would also like to, okay, so still the triangle is not there. So let me, okay, so let's call this point V. Let's take the point in which AC prime and BA prime intersect. Okay, so here is the triangle, ladies and gentlemen. Here is the triangle by means of which I shall be able to employ the theorem of Menelaus, so that these three lines are on a line. Okay, so let's introduce notation. Let me call this point U. Let me call this point W. Okay, so that the triangle is in counterclockwise fashion, UVW. You will see in a minute why. Okay, so let us apply. Okay, so the proof. So the proof. Why is this happening? Proof. By the way, it might be a good idea at home, when you're sitting at home and contemplating this treatment of the theorem of Pappus. You might perhaps like to think, I mean, what happens if these two lines do not intersect, if they're parallel? That is a point to consider. Of course, I mean, if these two do not intersect, you may find similar pair which will do intersect and do about the same job. And you might also consider the extreme situation when none intersect, no pair among them have this property. They're all parallel. Well, in that case, you will obtain a very special case of the theorem of Pappus. Well, that's something else. Okay, so contemplate that. What happens if they do not intersect? Proof. Okay, so let's use Menelaus in connection with UVW, triangle UVW. And of course, there are several lines with which you can do this. Let's first of all use the line BC prime. BC prime. Okay, so now that's the line. Okay, so with this line, I shall be careful. BC prime. Okay, because it is okay. So it is the line that contains X. So that you can actually write the following. So you can actually write BC prime. Well, this is of course the line XP. Okay, so let me write the theorem of Menelaus. So since BX and C prime are collinear, we come to the very simple conclusion that, okay, here it is, XV, XW times, okay, so that's what happens on the line on the side VW in connection with the point X. So what happens in connection with the next object, VW? The next object is, of course, WU. And, of course, what you've got is C prime. And C prime W by C prime, you know, U. And finally, BU. Okay, so I have chosen my notation carefully. So once again, you can really go blindfold. Okay, so that's what happens with BC prime. Let us see what happens with CA prime. CA prime. Well, in this case, I'm not going to go too deeply into it, but let me point out what it is. CA prime is this line. Okay, and in particular, it contains the point Y. Okay, so let me start with C, if you wish. No, let me start with YW, Y. So it says YW. In fact, you can go in a cyclic fashion. From X to Y, Y to Z, you will go from U to V, V to W. Okay, I've chosen the notation carefully. So, well, all the same, let me check my notes like what all bad teachers. Okay, so from C prime, you actually go to A prime. Okay, so that's W is replaced by U. Okay, so C prime is A prime. U is replaced by V. Okay, what is wrong with this? Okay, and B is replaced by C, V, CW is equal to +1. Okay, so that's what happens with CA prime, which is of course the line CY. Okay, so finally, well, not finally, but in this group as the last object, AB prime. So if you work with the line AB prime, let me point that out for you. AB prime is once again another transversal of the triangle UVW. So and it contains in particular the point Z. So you've got Z U divided by ZV times, instead of A prime, you've got B prime. So you can really go blindfold in this case. B prime W plus and A W A U. That's equal to +1. Well, that is a lot of information. That's a lot of information, but not quite enough, not quite sufficient. So, but however, these three, in a sense, constitute a group in themselves. So let me separate them from the following two. Now, I would like to use the theorem of Menelaus again. Now, with a different line. Well, rather obvious choice is the line K. When you apply the line K, okay, so what happens on the line VW? You've got C, so let's start. So with the line K, okay, so I have got what? Okay, so, well, okay, CV. CW, so let me start writing like that. CV CW times, okay, so what else do I have? CV CW, okay, next comes WU, so it is AW, AU, and finally, of course, BU. Now that's easy, BV, well, that's equal to +1 again. +1, and finally, of course, I will use the line K prime. K prime. Well, with K prime, I shall write not exactly the same equations, because you see the side VW contains this time no longer C prime but B prime. So you shall move a little bit B prime V, B prime W, okay, and C prime W, C prime U, and finally A prime, moving one back, U, A prime V equals +1. Okay, now, ladies and gentlemen, well, that's we do the usual thing. You multiply these first three equations, you get this interesting numerical object, and the rest, as for the rest, all you have to see is that you get the product BU, BV, CV, CW, AW, AU, and this first equation tells you that, in fact, the product of these three things is equal to +1, whereas the second tells you that this second column should give you +1. So from this, you come to the conclusion that XV, XW times YW, YU, ZU, ZV, as expected, is equal to +1. And theorem of Menelaus, use it backwards. Menelaus, used backwards, tells you that X, Y, Z are in fact collinear. Well, that is That's very nice. That's very nice. Once again, a pure application of the theorem of Menelaus. It gets you a very classical result. And in fact, it's not only classical, but we shall have, I do hope we shall have occasion this term or the next term to see what a fundamental and what a central position this theorem occupies in classical geometry. Okay, now, right. Ladies and gentlemen, there will be some talk. I mean, I will never I will never make a complete treatment of it, but as I promised all along, I will be talking a lot about this projective geometry thing that is the home for certain theorems, like the TEZER theorem, which quite obviously feel themselves not at home in the narrow confines of Euclidean geometry. So, we have already pointed out, we have talked about it, that this Euclidean geometry lives, in fact, in a larger geometry called projective geometry. And the projective plane is obtained simply by adding for every direction, you add a point at infinity to the Euclidean plane, blah, blah. We talked about that. This is one interesting property of the projective plane. In projective plane, you don't have parallel lines. Whenever you take two distinct lines, they will intersect. Okay, so if we imagine the projective plane as an extension of the Euclidean plane, two lines will intersect either as in the Euclidean plane, or they will appear not to intersect in the Euclidean plane, but they will then intersect at the points at infinity, the new ideal points. Okay, so there is no parallelity in projective plane. So any 2 points, so through any 2 points you can draw a straight line, and through any and if you give any 2 distinct lines, they will intersect in a point. Do you follow me? I give you given two distinct points, there is a single line containing them. Given 2 distinct lines, there is a point which is the intersection of them. Observe the way, these are very simple statements, yet conclusive enough. You notice that in these 2 statements, the second statement is obtained from the first one by simply interchanging the roles of the words point and line. 2 points determine a line, unique line. 2 lines determine a point. That's always the case. So the projective geometry will have this property that the theorems which are peculiar to projective geometry will have the property that they will preserve their validity when you replace points with lines, lines with points, and all the while retaining the property of incidence. Now, this is called duality. So, projective plane. So on projective geometry, interlude, let's say. So this is not really part of our, business, but let's take it as an interlude on projective geometry. So I pointed out that in projective geometry there are no parallel lines. So that's one interesting property. The second thing is that we expect is that the roles of points and lines should be interchangeable. Now, this Pappus theorem is typical of projective geometry. And I invite you to look at what happens if I replace points with lines, lines with points. Let's have a look. So what's the dual? The dual of the theorem of Pappus. The Pappus theorem. What is it? And knowing what it is it true? Şimdi, in fact, I can go directly to this statement. Look, belki buraya çevirebiliriz. Okay. So let's look at this. Given distinct lines, it says, let's make it points. K prime, lowercase k prime. Well, that's, by the way, there is a convention. There is a convention in projective geometry. Lowercase characters denote lines, whereas uppercase characters denote points. So instead of saying lowercase, I will take uppercase. So given distinct points k prime and distinct lines, instead of point A, I will take line A, line B, line C, and that's inside K. Well, we can't do it. Lines A, B, C, let's say with K contained in A, B, C. So I will take a point. Instead of line K containing the points big A, big B, big C, I will now take a point K through which will pass line A, line B, line C. Now I shall be drawing it. And similarly, instead of points A prime, B prime, C prime, you take lines A prime, B prime, C prime, and such that K prime, the point K prime, will lie on them. Okay, now this is getting difficult. If B, C prime, and B prime, C, now how are you going to do that? Well, instead of the line BC prime, you will take the point that's obtained by intersecting line B and line C prime. Okay, so you can write it as B C prime if you like. And the point, instead of taking the line B prime C, you will take the point that's obtained by letting B prime and C intersect. So these are 2 points. So these are 2 points, and there's a line going through them. And you have got similar situations: CA prime, C prime A, and AB prime, A prime B. Okay, so these are all pairs of points. Determine lines. Okay, now instead of big X, I've got small x. So I'm putting it handwritten X so that it's, and this is Y, this is Z, respectively. Then X, Y, Z are collinear or, of course, parallel. I'm sorry. Yeah, not collinear, but concurrent. Yeah, I'm sorry. Concurrent or parallel. Okay, here is the theorem. Now let me draw. Let me give you the picture. Let me give you the picture. I will try to be loyal to the original colors. Well, so what you've got is the following. So instead of lines k prime, you've got 2 points. Let's say k prime. Okay? And okay, instead of on the line k points A, B, C, you've got 3 lines here, so let me draw them. So let's say, for instance, the line A, the line B, and finally the line C, okay? And through the point K prime, I have to draw 3 lines again. So let's say, for instance, I have to be careful that, I mean, otherwise I won't get a good picture. So I'm being rather A prime. I'm trying to be careful. Okay. Yeah. Let us see if this will get me anything nice. Okay, so that's, let us see if I get something nice. And this is let this be B prime. And finally, okay, so let this be. Let us see if this gets me anything nice, C prime. It's difficult to guess, you know. Okay, so here we are. So for instance, that's AB, so AB prime and A prime B and AB prime. So they intersect in these 2 points, and there is a line that goes through them. We shall call that line Z. Okay, let's see if the other points are good. Okay, and A prime C and a C prime. Okay, so that's not too bad. A prime C and a C prime intersect. Okay, so if you like, I can write that A prime B, A B prime. Okay, so this is A C prime, A prime C. Okay, so these 2 points determine a line like this, and I call that line Y. And finally, please be good. Okay, yeah. Okay, so B prime C, and B C prime. Okay, so these 2 points determine a line, and do they or do they not? Well, I don't know. So they seem to be fairly. Okay, so here it is. So that's the line Z, that's the line Y, and that's the line X. So I expect them to be concurrent or parallel. That can happen too. So, is this true or is it not true? Well, this is true. This is true. This is true. In fact, you can. This is true. Okay, this is true. I would like to leave this as an exercise left to the student. You can actually look carefully at this picture, and you can find this is equivalent to, this is actually true, and in fact, equivalent to the theorem itself. That's a simple check. You can do it yourself. If you can't do it, come to me in my office hours, and I shall be delighted to point it out for you. That's the dual of the theorem of Pappus. I would like to conclude this lecture, perhaps a little prematurely, I don't know, but I think that's quite sufficient. I will ask you one question, and I will leave also that as an exercise. That is an exercise. I want you to go through this business of dualizing. That is replacing lines with points and points with lines. And while doing all that, not to lose count of things, it's a very good idea. It's a very good idea to replace lowercase characters with uppercase characters and uppercase characters with lower. So, so that you don't lose count of things, okay? So, for instance, you had the lines lowercase k prime. You replace them with points k prime, both uppercase. So, so that you've got a true list of what you are doing. I want you to use that technique exactly and to obtain, so left to the student again, write down the dual of TEZER. I want you to write down the dual of the theorem of TEZER and see for yourself that it is in fact the theorem itself. In fact, this is see that it is what you might call self-dual. Actually, so if you draw the diagram for the TEZER theorem, you will see that the dual is exactly the thing itself. So that's a rather interesting one. The theorem of Pappus is not self-dual, but you can actually prove it using you can prove the dual by using the theorem itself. So in a sense, there it is. So that's the end of the interlude. About projective geometry. So please make a list in your mind that of projective geometry, of this extended geometry, we expect two things: that there will be no parallel lines. Lines will always intersect unless they're identical. Okay, that's the one thing. So this, of course, in its turn implies that really the attitude of points towards lines is exactly the same as the attitude of lines towards points. So in projective geometry, the theorems would appear in pairs. Okay, so for every theorem, the dual of the theorem should be valid. The dual being obtained by interchanging the roles of lines and points while preserving the relation of incidence intact. So that's duality. So you've got a second property of projective geometry. If time permits, I shall talk about a little bit more about projective geometry, but these two properties are, for the moment, sufficient. So of the basic incidence theorems in Euclidean geometry, I've talked about the TEZER theorem and the Pappus theorem, both in their incomplete forms. And I've explained what it means, incomplete forms. I have provided you an introduction to the so-called projective geometry, and I have introduced the concept of duality. So that is, I suppose, quite sufficient for the moment.